Great, thank you. So let me join the other speakers in thanking all the organizers for making this conference possible. Today, I'm going to talk about geometry and entanglement. So in the last 25 years or so, we have seen the discovery of non-perturbatively precise theories of quantum gravity, such as the ADS-CFT correspondence and matrix models. And in each of these cases, the gravitational spacetime is emergent. It emerges holographically from the collective behavior of some dual degrees of freedom. And often these dual degrees of freedom have a non-gravitational description and therefore can be solved in a traditional way. This kind of emergent phenomenon is perhaps sharpest in ADS-CFT, where we have bulk spacetime in anti-de Sitter space that is emergent from a boundary CFT. But even in this case, a lot of issues about a lot of questions regarding the basic mechanism of how gravity emerges from the boundary has only been clarified recently. And in particular, I'm going to review some of the recent progress in understanding these issues. And we will see that insights from a quantum information perspective have been central. So there are a lot of connections between these ideas, and these connections grew out of a better understanding of what we call the fine-grained gravitational entropy. So here rho is the density matrix of some subsystem, and this entropy is simply the von Neumann entropy of that rho. This is often also called the entanglement entropy, and this entropy is fine-grained in the sense that it depends on the fine detail of the density matrix. So for example, if the density matrix rho is a pure state, then the fine-grained entropy is precisely 0, whereas the coarse-grained entropy could be non-zero. So far, everything is just standard definition of the von Neumann entropy. We will see what happens when we investigate what happens when we consider this in a gravitational system. I will focus on ADS-CFT, where we choose the subsystems simply to be subregions. So at leading order in the semi-classical expansion, so that when we consider the Newton's constant to be small, the entropy of a boundary subregion in the ADS-CFT context is simply given by the area of an extremal surface in the bulk. So in this picture, we have shown a single time slice of ADS-CFT, and the boundary has a subregion which I called A. This is simply a boundary arc in this picture, and its entropy, it is given by the area of extremal surface in the bulk, which is shown in blue and called chi A in this picture. This is similar to the entropy of a black hole, in a sense that the entropy of a black hole is also proportional to its area, its horizon area. And this is the original proposal of Ru and Takeyanagi. It has since been refined in various ways. It now is understood to work in not just static spacetimes, but also dynamical spacetimes. It has been generalized to incorporate high derivative corrections to gravity, and can describe Rayleigh entropies in addition to the von Neumann entropy. The quantum corrections to this formula has now been understood. We'll come back to this in a moment. And all of this has been derived using semi-classical gravitational path integrals, and that has been a major ingredient in all of this analysis. So as we have seen, the extremal surface plays an important role in understanding the gravitational entropy. And it also led naturally into the idea of the concept of entanglement wedge. Roughly speaking, this is simply a bulk space-time region that is bounded by the extremal surface. For our purpose, it's enough to focus just on a single time slice, where it is this shaded region between the boundary subregion A and the bulk extremal surface. So this turns out to be a very key concept in describing the subregion-subregion duality, which we turn to. subregion duality is a refined version of how we think of the bulk as being emergent from the boundary. It is the statement that if we have all the quantum information in a given boundary subregion, then we have precisely the amount of information needed to describe its entanglement wedge in this gray shaded region. In particular, we can consider an operator that is located in this shaded region, like the phi of x here. The statement is that it can be reconstructed as a boundary operator that has support only on the subregion that we started with on the boundary. In particular, it doesn't have to involve any of the CFT data on the complement of that subregion on the boundary. So this is called entanglement wedge reconstruction. This paradigm refines how we think of the space-time as being emergent from the boundary CFT. A striking aspect of all of this is that if this subregion duality functions as a quantum error correcting code. And the way we see this is that information that we have about the bulk is stored in a redundant way on the boundary. So in this picture, we have an operator at the location P, and we have divided the boundary into 3 regions, A, B, and C. This is therefore called the ABC example. And the operator at the point P can be reconstructed in 3 different ways as different boundary operators. It can be reconstructed as a boundary operator that is supported on the union of A and B, and also on the B and C, and also on the union of A and C. And these reconstructions are different, and therefore this is an example where information can be encoded in a redundant way on the boundary perspective. And this is a feature of a quantum error correcting code. So this is just another example where quantum information perspective has been central. Now, you can ask, how do we know that subregion duality works? The answer lies in the quantum corrections to gravitational entropy formula that I mentioned earlier. So let's come back to that a little bit. These corrections come from the matter fields and the gravitons in the bulk. And the answer is surprisingly simple. Instead of extremizing the area, we simply add a bulk entropy term to the area term and extremize the sum of the two. And in particular, this replaces the extremal surface that we had previously with a quantum version of it, a quantum extremal surface. So this is also called the quantum extremal surface formula. It matches a well-known one-loop result. It has been also derived by semi-classical gravitational path integrals. And in particular, this bulk entropy term is defined in the entanglement wedge, the shaded region. So roughly speaking, if we change the quantum state in the entanglement wedge, then it will show up, this change will show up in the corresponding boundary subregion, at least from the perspective of the entropy. And this strongly suggests that some subregion duality works. This line of argument can be promoted to a proof. So often this bulk entropy has a small effect on the leading area term, but sometimes it has a dramatic effect. An important example of this is the case of an old black hole. So let's consider a black hole that is built from a pure state, formed in a pure state. Hawking's calculation of the entropy of the Hawking radiation shows that the entropy will need to grow monotonically as a function of time. But unitary evolution suggests that at the end of the day, we must end up with a pure state for all the Hawking radiation. So the entropy needs to be 0 for the fine-grained entropy. So there's a tension between these two possibilities. And unitary evolution suggests we should follow the blue curve, the Page curve. Remarkably, the quantum extremal surface formula reproduced this formula quantitatively and agrees with unitarity. And what happens is that at the second phase of the black hole evaporation process, a new quantum extremal surface in the interior of the black hole becomes dominant. That is the blue surface that is perhaps visible on this, in this black hole. And remember that the entanglement wedge is defined as a region that is bounded by the quantum extremal surface. So now it contains an island, a green region inside the black hole. And remember that the subregion duality says that anything in an entanglement wedge can be encoded in a corresponding boundary region. This means that the island is actually encoded in the Hawking radiation, even though it is inside the black hole. So I have mostly focused on the fine-grained gravitational entropy, but a lot of progress has also been made with other quantum information theoretic concepts. I won't go through all of them. And a lot of this is quite gratifying, but many mysteries remain. I'll just end with a few open questions. One question is, it seems a miracle that gravitational path integral can work so well. It can be actually used to predict such a fine-grained quantity. What else does it know that we can use? Relatedly, we might expect that string theory could provide play a better role, a larger role in this story. So can we study all of this using string theory? To what extent we can think of the gravitational entropy as coming from, for example, stringy edge modes? Can we use holographic code to understand some of the properties of the bulk quantum gravity? Does this help clarify a lot of the long-standing puzzles, such as why physics under ADS scales is local? How do we use all of these ideas to understand physics behind the horizon and in cosmologies that, for example, resemble our world? And perhaps quantum gravity in the lab, doing some simulations and experimentally we can find some insight into these issues. So I'm out of time. Let me end here and thank you all.
Thank you very much for a nice talk. Are there any quick questions, perhaps in Zoom land? No? Oh, okay. Yeah. We have time for just one quick question. Okay.
Could you elaborate a little bit on what you think string theory might add to this picture?
So one puzzle, at least from a string theory perspective, is how precisely to define these entropies. Remember that there's a bulk entropy that I mentioned in the quantum extremal surface formula. That requires dividing the bulk into two regions, the entanglement wedge and its complement. But it seems at least an obstacle to think about that precisely in string theory, because strings are extended objects. So how do we incorporate that notion into all of this discussion? One thing is that a quantum extremal surface formula has been very powerful in solving the unitarity of the black hole evaporation. So how do we put all of that success into the string theory framework is what I have in mind here.
Okay, thank you. Let's thank Xi again.